Hanover Traffic Scenario for SUMO. And first of all, the little motivation why we need a new scenario, because there are already a lot of scenarios. But yes, I don't think I need to tell you, but simulations are essential to test various application and technologies, especially for use cases which are relevant for safety, or if testing is just quite hard in real world. Examples would be vehicle-to-X communication, or for example, traffic forecasts. And simulations currently mainly focus on motorized vehicles or rails and so on, trains, but there's a growing need to include also so-called vulnerable road users in simulations. So vulnerable road users include, for example, pedestrians, which are already well implemented in SUMO, I think, and also bicycles. And if you can look at the figure 1, you can see a model split and a model split forecast. So the first part is the model split of the year 2022. And you can see that there are already a high amount of VRUs inside. But if we now look at the model split forecast worldwide for VRUs, then you see that the amount of VRUs is increasing in the next years. And we have a so-called Vision Zero target in the EU, and this tries to eliminate all road fatalities until the year 2050. And one big problem here is that we have, in the last years, a stagnant fatality rate for bicyclists, and therefore it's very important to also include bicycles now in simulations, because they could profit, yes, very highly from new technologies, especially from safety technologies. And right now we didn't find any realistic scenario with real world data which really includes a high bicycle density. For SUMO and also for other simulators, there was no such scenario, and therefore our goal was to create such a scenario with a high bicycle density, but not only to include bicycles but also have vehicles inside of the scenario. And all of these should be based on real-world traffic counts, because, yes, for our use cases, it's important to have a realistic representation of the city. For the city, we choose Hanover, as the title mentioned already. We choose the city because it has one of the largest proportions of bicycles in the model split in cities with more than 500,000 inhabitants. And Hanover also provides traffic counts for bicycles and vehicles, which is not very normal in German cities. So first of all, how do we want to approach our goal? So in the first step, we selected and generated the map and the road network. In the next step, we did an analysis of the traffic counts we got from the city of Hanover. And then we did the parametrization of our scenario. And in the last step, we validated our Hanover traffic scenario. So first of all, the selection and generation of the map and road network. So in figure 2, you could see the region of Hanover we choose for our scenario. So it's not the whole city of Hanover, just a short part of Hanover. But this part has a very high traffic volume compared to other locations in Hanover, and also a very unique topology inside of Hanover, because it includes various primary streets which are highly used during the morning and evening hours. Then we have inside of this residential neighborhoods, and it's also located near to the city center. And all of these guarantee that there's always or mostly a very high amount of vehicles inside of the scenario at this part. But there's also this waterfront you can see there. And at this waterfront is a very focal point for cyclists, not only to go to their work and back, because it's very pretty there, but also to go for a bicycle ride or something like this. And therefore it guarantees also a very high amount of bicyclists in Hanover. So in the picture on the left side, you could also see these blue triangles, and these are our traffic counts we got. So these are 7 distinct traffic counts available, mostly located on the main streets, sadly. But yes, so just some network statistics about our simulated networks then. The total area is about 5.5 square kilometers. We have a high amount of exclusive vehicle and bicycle roads. Yes, the bicycle roads are doubled the size of the vehicles because at the most roads there are 2 bicycle lanes if there's 1 road. And there are also roads where both vehicles are allowed, and the scenario includes about 42 traffic lights. Yes, now I will continue how we get this part of Hanover inside of the SUMO simulator. So we did it as I think the most of us would do. We use the OSM web wizard, but one big problem with the OSM or with OSM map data is that the crossings and streets are not very well represented inside of OSM. And if you now look at figure 3, I don't know if you could see it very good here at figure 3a. Vehicles and bicycles were allowed at this crossing to go in any direction, and also the representation of the crossing itself was not very perfect. And if you would simulate it like this, then it would be a quite mess. And then we looked into Google Maps, and because I'm from Hanover, I also had some knowledge about these crossings. And then we also looked into Google Street View and used all of this to make the manual correction of all the crossing inside of the scenario, all the streets, and also the placement of the traffic lights and also the buildings. And also we removed the unused areas because to simplify the procedure, because it would take a lot of time to also correct those. So therefore there are no pedestrian ways, railways, private streets or bus lanes inside of our scenario. And figure 4 you could see the final result of our scenario. So in the next step we wanted to have traffic inside of our scenario, so therefore it was necessary to analyze the traffic counts and do also the parametrization of the scenario. So first of all, the traffic counts. As I told you before, we have 7 distinct traffic counts at distinct crossings, and they were all collected in May 2022 from 6 a.m. to 7 p.m. and the data has a 50 minutes resolution. And each traffic count is described by a so-called turn count for vehicles and for bicycles. So an example of such a turn count you could see in figure 5 above. So a turn count says which vehicle or how many vehicles go from one lane to another lane, and therefore you have a really good resolution of one crossing inside of your traffic counts. For example, here 44 vehicles went from the southern side to the western side. And so all of this leads to 86 distinct turn counts we had for the simulation or for the parameterization and trip generation. And we did this with the SUMO tools, so the route sampler and the random trip script. And in figure 6 you could see the traces inside of the traffic counts. So yes, in blue there are the vehicles, in orange the bicycles. As assumed, there are more vehicles than bicycles available, but you can see this pattern that in the morning there's a peak, and also in the evening. Then in the middle of the day it's a little bit lower, and in the end of the day and beginning also. And it's nearly the same for bicycles, but here's a short difference because in the end of the day, yes, a lot of people will go on their bike to make a good trip or something like this. So after we generated our routes inside of the SUMO scenario, we first of all parameterized the scenario. So the start and the end value are representative for 6 a.m. and 7 p.m. exactly like in the traffic count data. Our default step length is way shorter than the default value, so we selected a value of 0.1 seconds, but we also tested shorter and higher values. So we selected this value because our use case for the scenario is V2X communication, and in V2X communication a resolution of 0.1 seconds is essential because of the generation rules for messages. Also we activated the sublane model for this scenario, because as most of you may know, bicycle will never wait behind each other at a crossing. They will always wait beneath each other, also overtake each other in a single lane and so on. And we also wanted to minimize the impact of junction blocking vehicles. So in real world you would also see things like you try to avoid a vehicle which is on the junction and no one will wait when he has a green light. And then also a very important parameter was the car falling model. So for the vehicles, we choose the default Krauss model. But for bicycles, we presented last week our realistic bicycle dynamics model. So this is able to make a more realistic longitudinal behavior of bicycles inside of the simulator. So more realistic acceleration and deceleration values and also speed values. And we used also the Krauss model, so it's not only tested on our new model. Then you may already saw there was another parameter called the rerouting probability. This parameter allows you to reroute your planned route if there is a jam on your route or if it takes a shorter time if you choose a new route. And this is, yes, behavior like real-time navigation on Google Maps. And without using this parameter, you can see one result here down for the vehicles. The whole scenario was jamming because there were some crossings where it was necessary to avoid the vehicles there and they needed a rerouting. And if the time of the day continues, there was so much jam in our scenario that it was not possible that any vehicle was turning anymore. And yes, to optimize such a parameter, it's an optimization problem, and we choose an objective function for this. We used a combination of 3 different metrics, which are all weighted equally, and also bicycles and vehicles was weighted equally afterwards. First of all, we choose the normalized root mean square error for this. We selected this one because related work like the inter scenario also used this one to find the perfect rerouting probability. But when we used only this value, we had this problem that the peaks of the day were represented very bad. The whole day was okay, but in the peak times it was bad. And especially for our use case of V2X communication, it's important to have also the peaks. Therefore, we also use the absolute traces difference. So the difference of the whole day between simulated and expected traces, and the maximum time slot difference, because we also wanted that at each time slot inside of our simulation, it's as perfect as possible. And therefore, we selected the highest difference at one day at one time slot here. And as you can see now on the figure 8, these are the results of our scoring. So for low values, we could not reach the perfect traffic amount, but also for very high values, we could not match the traffic amount of the traffic counts, because then most vehicles will reroute and then you will see that they are at other crossings and so on, and that's not what we wanted. So, but there was a quite good field or range of values, and we selected a value of 0.22 equal to a probability of rerouting to 22%. So in the last step, we did the validation of our scenario. So we compared again with our real-world data. And in the picture above, you can again see the comparison between simulated and expected traces. So in orange, the expected values from the real-world traffic count data. And in blue, the simulated amount of traces. In figure 9, it's for the vehicles. In figure 10, it's for the bicycles. And as you can see, it fits quite well to the distribution. We have always a little bit less traffic compared to the real world. One reason for this is the impact from bicycles to vehicles. For bicycles, it's a little bit higher compared to the vehicles because bicyclists, yes, tend to break rules at crossings. And it's, yes, not possible in simulation to have a such high amount as in real world which cross the green light. So therefore the amount of bicycles is always a little bit higher, or sometimes for the peaks also delayed a little bit. But yes, we wanted to be honest, and we don't have only these best cases, and not every crossing was able to represent perfectly. So we looked at each turn count inside of our simulation and in the real world, and compared them with the expected and simulated values. Of course, most of the crossings are represented like the best case, and we have a very good distribution compared between simulated and expected values. But there are also some worst cases where it was not possible to recreate the amount of traffic inside of the simulation. So for example, we have here one crossing or turn count. This was a left turn without a green or explicit green light. And here it was very hard in simulation to have the same amount of vehicles going left as in the real world. So in this case, there was often a rerouting because there was a jam at this crossing. Now also, yes, some of the limitations of our scenario. So yes, as you see in the first picture of the location of the traffic counts, we have a very geographic concentration of these traffic counts inside of our road network. So we want to have more data, but there's no data available, sadly. And therefore, yes, without this data, it was not really possible to also validate the residential areas of the traffic amount and also validate the patterns in all the locations we wanted to simulate. Then there's also, yes, an unknown part. So we got the traffic counts from the city of Hanover. They told us how they collected them. The collection was based on video analysis. And as most of you may know, video analysis is always very sensitive to weather, light conditions, the technology which is used to, to get the number of the vehicles inside. And also, if you now assume there's a big vehicle in front of a bicycle, you will never see this bicycle at this video. And therefore, they could not report us any error margin inside of these traffic counts. So we have to trust them that the data is accurate enough. Then there was also no dynamic traffic patterns inside of our data. So we could not evaluate if the traffic flow itself is really accurate. So there was no data about the average speed of vehicles or how long a vehicle would take from one point to another inside of or in the real world. So therefore it was sadly not possible to also evaluate these things. So last but not least, a short summary. The first thing is that we have now a realistic representation of the road network in Hanover, able in simulations and also in SUMO. And then the next summary is we have also a realistic, or as realistic as possible, a representation of bicycle traffic and vehicle traffic in Hanover now in simulators. And the last one is more like an information. All of this, what we have done, is open source available. You can see it under the GitHub link or just scan the QR code. Yes, thanks a lot for your participation. And if you have any questions.